Everybody. The next chapter we're going to talk about is gases. So, the first thing that I want to do is talk about first the three states of matter that we're familiar with: solids, liquids, and gases. So, the first one, if we remember, we have our solids. Okay. These guys are very, very closely compacted. The thing you also need to remember is when something is matter, it is always moving. So my atoms and molecules are always moving. In my solids, they are tightly compacted and they are vibrating very, very slowly. Okay. Then we move to my liquids. These guys are a little bit further apart. Some are touching, some are not. However, there's a little bit more space in between, so they're moving a little bit faster and they're moving a little bit more freely. Whereas my gas or my solids, they're so tightly compacted that they can't really move without moving the other. So they move very, very slowly. My liquids, they move a little bit more freely because they have a little bit more freedom. My gases are very, very far apart. They really don't touch each other. When they do touch each other, they bounce off of each other immediately. They don't like to stay very close to each other at all. Okay. So when we talk about gases and we think about those things, there are three main characteristics of gases. They're easily to compress, meaning I can take something like if you think about a gas as in a syringe, I can smash that syringe down and compress it into a smaller space. Gases also expand to completely fill the container that they're in. So if I take a look at my bottle right here, if I were to throw some air into it, okay, that air is now filling this bottle up. If I were to take the cap off and spill that air into the room that I'm in, my new container, those air particles move out as far as they can and take up the entire room. They fill the container that they are in, which means their volumes also change because now the volume of that gas is the volume of this room. Gases also occupy more space than liquids or solids. That's why they fill their container. So if a gas is in a very large container, the volume will be very large. Whereas if I take my cup of water and I spill it on the floor, it still occupies the same amount of space as it did in my cup. When we also talk about gases, we talk about pressure. Okay, pressure is the force per unit area. So if you think about these gases, these gas molecules running all over the place, when the molecules hit the side of the container, that is pressure. So the more times the molecules hit the side of the container, the more pressure something has. When we talk about pressures, we have to talk about units on pressure. The unit that you're probably familiar with is PSI because that is what's on your tires. If you drive, you know that you need to make sure that you have the correct PSI in your tires. PSI stands for pounds per square inch. Obviously, inches, we don't use the English system in science, so we use our metric. There's a few different units of pressure that you should be familiar with. Atmospheres, which is ATM, millimeters of mercury, which is also abbreviated mmHg. We have torr. There's really no abbreviation on that one. And then we also have kilopascals, and that one's abbreviated kPa. The other thing when we talk about gases, we got to talk about temperature. Usually when you think about temperature, you're referring to it as how hot or cold something is. Okay? Whereas temperature here, it is how hot or cold something is, but we'd be a little bit more specific in terms of what temperature is. Temperature is the measurement of average kinetic energy of the particle. So if you remember what kinetic energy is from last year, kinetic energy is moving energy. So the faster that I'm moving, the more kinetic energy it has, which means it's going to have a higher temperature. So when I came in this morning, it was a little bit cooler. That means that those molecules are not moving as fast, which means the temperature is very low. They have a very low kinetic energy. You usually are very familiar with the units of Celsius or even Fahrenheit. In chemistry here, our thermometers don't read in Fahrenheit. They almost always read in Celsius. However, when we're doing gas law problems, we don't even deal with Celsius. We deal with Kelvin. Kelvin is another temperature scale. This one, we have an absolute zero, which means there is no negative numbers in the Kelvin scale. At zero, that means that the molecules are not moving. That's why we refer to it as an absolute zero. When converting from degrees Celsius into Kelvin, it makes it very, very easy. All we have to do is add 273. So if I give you a degree Celsius, all you need to do is add 273, and that will get me in units of Kelvin. So this problem right here, at 27 degrees Celsius, I want to change it to Kelvin. So Kelvin is equal to my degree Celsius, so that's my 27 plus 273. So I have 300 Kelvin here. And we don't typically say degrees Kelvin, we just say Kelvin. And the abbreviation is just a capital K in that case. When we also talk about gases, we also kind of have a base, we need to have a baseline. And this is what we refer to as standard temperature and pressure. These are conditions usually at sea level, okay? So when I say we're at STP, or standard temperature and pressure, I am telling you what the temperature is, and I'm telling you what the pressure is. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Now, the tricky thing is, I just told you that when we deal with gases, we don't deal with the Celsius. We need to convert them into Kelvin. So what would my standard temperature be at 0 degrees Celsius? What would it be in Kelvin? Reminding you, all you have to do is take that degree Celsius and add 273. So standard temperature is 273 Kelvin, or 0 degrees Celsius, because remember, they're the same exact thing.